Good evening, everyone. So today we'll start with the lecture 10 of stochastic process. So in the last class, lecture 9, we discussed about discrete time Markov chains. So let me give a quick recap on what we discussed. So discrete time Markov chains are used to model the states of a process of a system, uh, where the states can take random values at different times depending on how the state how the system progresses according to time. So one of the system that we took last time was a frog jumping on lily pads, randomly jumping on the stones. So we put some probabilities on how the stone would, with what probability the frog would jump from one stone to another. And we tried to find out uh, as time as time increases, mm, uh, what is the more the limiting probabilities of where the frog is most probable to be found, on which rock it's more probable to be found, and those kind of stuff. We didn't answer those, but that is what we were interested in. So last time we just did the basics of introducing Markov chain. So what are, uh, what are we interested in Markov chain is these three things, like uh, what is the state of the system, with what probability you'll find the system in this state after some n steps, 30 to 50 or some 100 steps. Then what are the limiting probabilities? So what is the probability that you'll find the frog at some particular step that you at what one particular state that you want, given that you allow the system to run infinite amount of time. And then we also wanted to answer some questions like, uh, will the system visit each and every state always, or are there some states which the system visits once and does not visit again? So those kinds of stuff. Then we gave a definition of Markov chain. So whenever you come across the term chain, it basically means that the state space is discrete. So you have discrete values that the state can take. It could be finite or infinite. Infinite, but it should be countably infinite. You have discrete state space so that you can count them. And um, uh, what we were interested in is discrete time and discrete state space. So there are three things actually which you need to define a discrete time Markov chain. So that is the state space. The state space is all the values that the state of the system can take. Then initial probabilities. So with what probability the system starts at what state? That probabilities with the initial probabilities. And then we got to the transitional probabilities. So the transitional probabilities were, okay, so given you are in some state, what is the probability that in the next step you will be in some other state? Those are the transition probabilities from each and every. So you have to make a transition in each step. That is the constraint that I've put on the system, which you want to model it as a Markov chain. So the main property of Markovity in a system comes in, given the whole history, um, you want to find the probability that the next step is J. Just depends on what the previous step was. It doesn't depend on what the whole history was. The whole history doesn't matter. You can take any number of paths to reach the just immediately previous step. The probability will remain same. That is a Markovity probability. So mm, yeah, then we saw transition probabilities, initial uh, probability vector, and then the transition probabilities which you can put it down as a matrix, and then the matrix has some property that the mm, rows add up to one. The row sum is one. The column sum could be one, but it doesn't matter. So if the row sum is one, then it's known as stochastic matrix. If the row sum and the column sum is one, then it's known as doubly stochastic matrix. These things we will use later as we try to prove some stuff. Then we try to find the joint distribution of the probabilities of states. So just not the so Markovity, you start off with conditional probabilities. So the transit probabilities are conditional probabilities. So given that you are in state I, what is the probability that you'll end up in state J? Those are the transition probabilities that we have defined above. But you don't just want the conditional probabilities. You might sometimes need the joint probabilities. So we find out a property of how to find joint probabilities. You just multiply the transition matrix with the initial vector, and then you get the probabilities uh, at each step. Yeah, and then we found the joint probabilities for n steps also, where you just keep on multiplying the transition probabilities from each step to each step with the initial probability of you finding it at x0. We took an example and we found out all the steps that it takes to calculate those things. Then we went into something known as multi-step transitions. So what if you don't have just the immediate next state, but you have some condition that, okay, at second step I was at this state. What is the probability that condition that at the second step you were at state I? What is the probability that at the 10th state you'll be at state J? So those are multi-step transitions. Now you can take number of paths to go to there. But this also we saw last time. We calculated it as you just need to multiply the transition matrix n number of times, the number of steps that you need to uh, go forward for the calculation, and then you multiply it with the initialization vector, and you get back the uh, probability vector for all the states at nth time, conditioned on uh, previous step. Here we use the property of homogeneity, which means that the transition probability matrix does not change at each and every step. The transition probability matrix is fixed for all time. That point I forgot to emphasize on. So the here we use the property of the Markov chain, which is known as homogeneous. So basically, the system is homogeneous. Matlab, you can say that the transition probabilities remain same at each and every time t. They don't change with time t. So it doesn't matter if you're looking at the second step to the third step. Even the 10th step to the 11th step would have the same transition probabilities. Even 100 step to the 101 step would have the same transition probabilities. So under those conditions, you can multiply the uh, transition matrix n number of times to get the n step transition probabilities. Okay. So today we'll be starting off with some examples of Markov chain. So the first example is a Bernoulli process. So Bernoulli process, so you have the parameter P. So I just say that let the parameter P be something between 0 and 1. P could be anything between 0 and 1. So what you do is you repeatedly flip a coin. You repeatedly flip a coin whose probability of getting a head is P. So you do this n number of times, like you do it repeated number of times. So the times are at times 1, 2, 3, and so on. Okay, so now I'm defining a random variable. So let xn be the number of heads at time n. Right? So then the claim is that this stochastic process, the number of heads is a Markov chain. Okay, but to define a Markov chain, we need to define what three things. So first is the state space. So the state space. So initially you'll have 0 heads, 0. Then you keep on flipping the coin. At some point or the other, you will hit a head. So the number of heads will go to 1. And then you again keep on flipping the coins. Again, it will go. You'll hit an head. You will get 2 heads total. Number of heads that you have hit till then. You continue this. So the state space is the whole natural numbers with the number 0. So positive integers. Now suppose I give that x0 equal to 0. Suppose I give this. Then, or no, supposing you did not give x equal to 0. When you start the experiment at time 0, no heads have been seen. So x0 is 0. So the initial probability vector is basically 1, 0, 0, and so on. So all zeros. This is the initial probability vector. Now the transition probabilities. So Pij. So basically you can either go from 0 to 1, 1 to 2. It can only keep on increasing because the number of heads you see, you don't see a negative head anytime. You always see a head or you don't see head. So it is 1, 0. So you will see a head with probability P. So that is P. So if you see a head, then the state that you are in, the next state that you will be in is incremented by 1 because now you've seen an extra head with probability P. And you will not see a head with probability 1 minus P, which implies that the number of heads have not changed in the time T. So if J equal to I, 0, otherwise. You can't jump 2 steps at same time because you flip a coin, you can't see 2 heads. That is an impossible event. So yeah, this is your transition. So this is the state transition matrix. This is the state space, and this is the initial probability, initial state properties. So next we'll start drawing the state transition diagram for this. So yeah, state transition diagram. So you plot out all the states that are possible. So state transition diagram. So 0 state is possible, 1 state is possible, 2 state is possible, 3 state is possible, 4 state is possible, 5 state is possible, and so on. Now, so the state transition matrix tells you that okay, if you're at 0, you go to 1 with probability P. But you stay at 0 with probability 1 minus 2 because if you land a tail, then the number of heads are not increasing. So you land a tail with the probability of 1 minus p. So you going from 0 to 0 is, then you go from 1 to 2 with probability p. You staying at 1 with probability 1 minus p. Going from 1 to 2 is probability p. This keeps on happening. P and 1 minus p, p and 1 minus p, p and 1 minus p. Sorry. Sorry. So whenever you see that the state transition matrix should have the row sums as 1. So what it means is the outgoing links, they should add up to 1. So you see that from 0 with probability p, you go to 1. With probability 1 minus p, you come back to 0. So in the next step, with probability 1, you're going somewhere around there. You're not like skipping the step. There is no skipping steps in Markov. Skipping a step could also mean that you are in the same loop, but it has to be assigned a probability with what you just stay in that loop, stay in the same state, or you go to the next state. So the thing to check from each and every node, if you have drawn a correct state transition diagram, is to check at each node, check the outgoing nodes. The sum should be 1. That is a sanity check that you can do to see that you have drawn the correct state transition diagram. So this is the state transition diagram. Yeah, so this is an example of Markov check. We will give one more example. So one more example is a simple line. So again, I define a parameter E, and now, uh, okay, it is a simple random walk. Simple random walk is basically you have xn. So let me put it this way: simple and work, but I'll be using gambling to explain the concept of simple and work. So basically, uh, each time you bet one at each time instant. So you have time instance. 1, 2, 1, 2, 3, 4, 5. At each time instant, you bet $1, 1 rupee, right? So when you bet 1 rupee with probability P, you win 1 rupee, and with probability 1 minus P, you lose 1 rupee. So basically, what is happening is you have 1 rupee with you. So suppose you bet 1 rupee in that, you get an extra 1 rupee with the rupee you have given to bet. If you lose the bet, then you're taking away the bet. You're losing the bet. You don't win anything. You just lose the bet. So what happens is every time you win, to your whole amount of money that you have, 1 rupee gets added. If you lose, then 1 rupee gets subtracted from your whole amount of money. So basically, that is what happening in this gambling setting. So now uh, XN is the total amount of money you have after n steps. Here you can go to negative rupee. You take some loan from somewhere and you are betting even though you don't have money. That kind of thing also is allowed in simple and work. Basically, you're taking credit from someone and putting in money so that you in the future you plan to win some amount of dollars. So those all are allowed. So basically, your state is all the negative numbers -3, -2, -1. So what the negative numbers indicate in the gambling thing is that you are in loan from someone. So you're taking money from someone and then you're putting it to bank. Okay, 0. So we are broke. Then you have positive numbers. So which means that you are winning. So this is the state space, the whole integers, the whole integers. Okay, so starting new could be any you can start at any given. So you can come with 3 rupees, you can come with 100 rupees, you can come with 1,000 rupees. It doesn't matter. You have some vector which says that okay, with probability this you start off with this much amount, but you have a vector that is given. So next, the important thing is writing of the transition. So you can just take that okay, x0 equal to some a being some number that you want. It could be 0. It doesn't matter. So even if you come with 0, you take loan from someone and you put it, and then you get 2. And now you win it all rupee, and then you can the loan that you've taken for 1 rupee, you can give it back. Now you have just 1 rupee. So it doesn't matter where to start from. So this is the gambling setting. So yeah. Okay, so now the state transition matrix. So PIJs are basically so with probability P you win. So you go from J equal to I plus 1. With 1 minus P you lose. You go back a previous step. So J equal to I minus 1. 0 elsewhere. Otherwise, so you can't basically jump 2 steps of forward or 2 steps back. You can go 1 step forward, 1 step backward. That is basically what a random walk is. So to draw it in a time axis. So suppose you start at some A with probability P you go up, with probability P you come down, 1 minus P, you can go down again, you can come back. So this is one of the sample paths that a random walk is. Could be something like that. Continue going on. It again doesn't matter. Okay. So Now, so this is the state transition matrix. State transitions. Okay. Then you have state transition diagrams. So state transition diagrams are, so you draw out the whole state. So you have basically the negative numbers, -3, -2, -1, 0, 1, 2, 3. Okay. So suppose you start with $1, right? So with probability P you win one. Suppose you start 1 rupee, with probability P you win 2 rupees, with probability 1 minus P you win nothing. You win you lose 1 rupee, so you go back to 0. Same with 2. With probability P you gain 1 rupee, so you go to 3. With probability 1 minus P you go back to 1. So 3 1 minus P you go back to 2. Now with if you're at 0, with probability P you gain. If you are at 0 with probability 1 minus P, now you own the casino. So minus P, you already own someone and you already owe someone, and suppose you used his money, someone else's money, to win, you basically go back to being 0, and this kind of thing continues throughout. So this is the state transition diagram. So actually the interesting things in the simple random walk is, or this is also known as gambling ring, last is what happens in the long run. So you keep on gambling. So what happens? Do you end up with huge amount of money, or you always end up broke, or the probability of you going broke is greater than the probability of you uh, winning? So these kind of things depend on how the system is modeled. So if you know how the system is modeled, you can uh, uh, give probabilities on how long will it take. Okay, if you take broke, how long will it take you to go broke, or eventually will you win? Those kind of stuff. So uh, a more important special case is that when p is equal to half, then you call it a simple symmetric random walk. Then you have equal chance of winning and losing. So we'll look into it later when we talk about random walks. So this is the basic introduction to random walks. Okay, we'll give third. This is the third example. So this is RNFS earn. So basically what you have is you have D balls and two ones. So basically you have two ones, and among them you have put D balls. However, total amount of balls in both the ones are D. So here you have 5 and 4, so 9 balls you have in these two ones. Okay. So next is you put a ball from this urn to this urn. So at each step, what you do is you randomly pick a ball. Irrespective of the urn, you pick a ball from both the urns uniformly random, and you just shift the ball to the other. It the it need not be of this urn or this urn. Just out of those 8 balls, you pick a ball. Suppose the ball is at urn 1, you shift it to urn 2. Suppose the ball it has urn 2, you shift it at urn 1. So let me call this uh, urn 1 and urn 2. Okay. Yeah. And then you keep on continuing this. At each step you do this. You randomly choose a ball, move it around. So here the important thing is to know which what is a Markov chain. So I keep track of xn. This is the number of balls in urn 1 at time n. This number of balls at urn 1 in time n is a Markov chain. Okay, so for that we'll need to first write the state space. So the state space you go from, you could have no balls in urn 1, all the balls could be in urn 2. But then if all the balls are in urn 2, then with probability 1 you are picking some ball that is in urn 2. So then in the next step you are putting it back to urn 1. So now you have a ball in urn 1. Now if you have a ball in urn 1, with some probability you'll pick the ball that is in urn 1. But then because you'll put it back in urn 2, it'll again go back to 0. So those probabilities are there. So but more probability is that you'll pick a ball that is in urn 2 because urn 2 has more number of balls. So you'll put it in urn 1. So it can be 2. The worst case that could happen is all the balls you have chosen from urn 2, and at some point of time, all the balls have come back to urn 1. So that is D. Right. So the state space is finite. So in the previous two examples, what we saw, the state space was infinite. Here, what we are saying is the state space is finite, 0 to D. You have an upper limit on what the state should be. Right. Okay. Now, we have done the state space. The initial distribution could be anything. It could be you could the initial distribution could be anything. The D length vector sums up to 1. So you could randomly put the balls in urn 1 and urn 2. So you could get some number of balls in urn 1, some number of balls in urn 2. Or you could have a strategy where you put all the balls in urn 2 in the initial state. So then you, with probability 1, you'll have 0 balls in urn 1 and 0, 0 for all. So it doesn't matter. The initial vector doesn't matter. Next, you have transition probabilities Pij. So Pij is equal to, okay, uh, okay. So okay, let's see. If you are at if there are eyeballs in urn 1, now if you select a ball from here and put it here, then you in the next state you go to I minus 1. So j equal to I minus 1. Right. In the next step you're going to I minus 1. So what is the probability? The probability is that you choose a ball from urn 1. If you choose a ball from urn 1, then it is guaranteed going to urn 2, and then you have decreased in the number of balls by 1. So the probability of choosing a ball in urn 1, when you know that there are I balls in urn 1, is I by D, because you're choosing it uniformly randomly. That thing is important. That is important. Uniformly random choosing the ball. This is the important part. That is how you get the probabilities. So now suppose you don't choose a ball that is in urn 1, you choose a ball in urn 2. That puts a ball in urn 1. So there in that step you go from I minus 1 to I plus 1. So j equal to I plus 1. But now you're choosing in urn 2. You know there are I balls in urn 1. So there are D minus I balls in urn 2 uniformly. 0 otherwise. So yeah, let's draw the state transition diagram for some 5 balls, and I say that some 5 balls. So let D equal to 5. So you have 5 balls. Now what is the state transition diagram? So you have 0, 1, 2, 3, 4, 5. Okay. So if you're at 0, with probability 1, you'll go to 1. So let's see who does that come. So I is 0, then j equal to -1. That is not in the state space, but you see that the probability goes to 0 because I is 0. I is 0, 0 plus 1, so j equal to 1. So the next step is 1 with probability I is 0, so this becomes 1. So with probability 1, you go from 0 to 1. Okay. Now I is 1. I is 1, then j equal to 0 with probability 1 by d. So it's 1 by 5. D minus I by d. I is 1, so it's 4 by 5. You go to 2. Um, Next, same thing from 2 to 3. So 2 to 3. So I is 2. 2 minus 5 by 5. 3 by 5. 3 to 4. I is 3. This is the going right. So um, 4. D is 5. 5 minus 3 by 5. 2 by 5. And 1 by 5. 2 to 1. So you can basically look at the outgoing nodes and say that, so this is 3 by 5, so this will be 2 by 5, this will be 3 by 5, this will be 4 by 5. If you have 5 balls in on 1, then with probability 1, because you're choosing one of the balls exit, that will be pakka in on 1, it will go to 1, so it will be 1. So this is the state transition diagram for RNFS. So yeah, these are the examples of Markov chain. Okay, so last class we learned about how to calculate one-step transition probabilities and how to calculate n-step transition probabilities, right? Uh, so so mhm, today I'll be giving a set of equations known as Chapman Kolmogrov equations, uh, which also define n-step transition probabilities. Uh, for calculating these instant transition probabilities. Okay, so we are still in. So we are still in. So this is an extension of the multi-step transitions that we are looking at. So your one-step probabilities are one-step transition probabilities are your Pij condition probabilities. Now let the n-step transition probabilities be Pijn. This n defines the number of states that you have. So basically what I'm saying is uh, Pijn equal to probability that x n plus m equal to j given xm equal to y. For some n greater than or equal to 0, I comma j greater than or equal to 0. So if you see that Pij1, that will be just equal to Pij. So the Chapman, so now we'll discuss about Chapman Kolmogrov equations, which help us to calculate this n-step transition probability. So help us to calculate this n-step transition probabilities. So the Chapman, first write down the Chapman Kolmogrov equation. So that is Eij n plus m equal to summation k equal to 0 to infinity Ik n Kjn. So here we are taking that the states value can be all the positives. So 0 to infinity are the states that you can take. So this is for all n comma m greater than or equal to 0 and all I comma j. So this actually is very easy to see. So I'll just prove this first. So you have Ij. So this is the Chapman Kolmogorov equation, which says that the transition probability of going from in for going from I to j in n plus m steps is basically summation of going from I to k in n steps and k to j in n steps. So that k could be you need to calculate the probabilities for all the states that you can take. So you pick a k and then calculate the probability going from I to k and then k to j. I to k in n steps and k to j in m steps. Uh, and now you just vary the k. As you keep on varying the k, you will see that you're covering all the sample paths. Those are possible for you to go from I to j in n plus m steps. That is the basic idea behind the Chapman Kolmogorov equation. So what I'm saying, okay, let me just draw this out. So in okay, so this is time. These are the states. Suppose this is I state and this is j state. So now you want to go from I to j in n plus m steps. So what you do is you pick some state k, which is a variable. So this is k. This state is variable. You can push it up and down. Suppose for now I fix k to be this step. Then you calculate all the paths that you can go to k. These are not the paths you need to be hardcore. So calculate all the paths that you can go in n steps from I to k, and then m steps from k to j. And now if you keep on changing the k, you'll see that you have covered all the sample paths that are possible for you to go from I to j in n plus m steps. That is the basic intuition behind the Chapman Kolmogorov equation. Okay, so now for the proof. So you want to go from I to j in n plus m steps. So basically what you're doing is x n plus m equal to j given x0 equal to a. So basically here you're using a homogeneity a little bit because looking at 0 to n plus m is same as looking from k to k plus n plus m. It doesn't matter. Okay. Next, in the total law of probability, you have you can add the event that at xn I'm at k step. Now k steps I'm iterating through all the states that xn can take, conditioned on x is equal to a. Then we have summation k equal to 0 to infinity. Now using Markovity. Oh, now using the definition of conditional probability, you can write this as probability of x plus nn equal to j given xn equal to k, x0 equal to I into probability xn equal to k given x0. Um, then now you use Markovity. So basically this is you no need to care about the history, just the immediate history is enough. So this is summation k equal to 0 to infinity. P, you are going from k to j in m steps. And this is you're going from I to k in n steps, which is basically summation k equal to 0 to infinity probability I k n probability k j n. So this is the proof for the Chapman Kolmogrov equation. So which boils down to matrix multiplication. So in the last class we saw that if you want n step transition probabilities, you can just consider it as a matrix. You don't need to find each and everything. So if you treat p n plus m as the n plus m step transition matrix, then you can write this as pn into pn. So where here pn is the n step transition matrix. And here this dot implies matrix multiplication. So this is everything about multi-step transitions. So now you know how to calculate multi-step transition probabilities. You can use Chapman Kolmogrov equations, or you can just use the matrix multiplying property, which comes from the Chapman Kolmogrov equations. So next we'll be going into a topic known as communication. So communication or two states I and j are accessible to each other. Then we say that I and j communicate with each other. So what does this mean is, so okay, communicating classes. So we say two states are communicating if for some, so let the two states be I comma j. So I and j are communicating if for some n greater than or equal to 0, Pijn is greater than 0, strictly greater than 0, then we say that the two states are accessible to each other, or the two states communicate. So what this means is, so there is a way of if you're at state I, there is a positive probability of you reaching j from I in n steps for any n. That n could be any n, how large ever it may be, how small it may be. Then we say that I and j communicate with each other, and we denote it as I communicates with j. Now, okay, I'll come to a subtopic which is known as equivalence relation. So my goal is to show that communicating classes or communicating states is an equal, or communication is an equivalence relation. So what does equivalence relation mean is that, so you have a reflexity, so which means A equal to H and B 2. This is the relation that you're going to test. The relation here we'll be testing is the communication relationship, this relationship. Okay. Next is uh, symmetry. So if A equal to B, if A equal to B implies B equal to B. C is transitive. So if A equal to B and B equal to C implies A equal to C. So if any relation which satisfies these three properties, then we call it as an equivalence relation. So communication is an equivalence relation. We'll show that. So first we'll take reflexivity. So I communicates with I. From the definition, you can see that if n equal to 0, then pii that will be greater than 0. It will be 1 because you are at the same 0 steps. You have not taken steps, you are at I. So I communicates with I and vice versa. So this is true. So from the definition, we can say that it is a reflexive property. 2. If I communicates with J, then J communicates with I. So because you have this whole thing of symmetry, um, so if I communicates with J, then Pijn is greater than 0. So that means you'll also have a sample path which will go from J to I. In some n steps, it might not be the same n, but there'll be an n such that you have some positive path. So these two are trivial. The third one is if you can go from I to J, and if J can go from J to K, then you can go from I to K. This basically uses the Chapman Kolmogrov equation. So suppose I communicates with J and J communicates with K. What does this imply? There exists M and N such that Pijm greater than 0 and Pjkn greater than 0. This is from communication. Communication. So we know these two happen, right? So we need to show that Pik m plus n. This is also greater than 0. But we know that this is to be 0, sum s equal to 0 to infinity. Ism Pskn. Now these all are positive or non-zero numbers. So out of all this state, there will be a state j. So it will be less than, because I'm adding all positive numbers, I'm removing all the positive numbers which I'm adding. So it will be always less than or equal to, because if everything is 0, then it will just be equal to Pijm Pjkn. Now from the definition of coming, we know that these both are greater than 0. So multiplying something greater than 0 is greater than 0. So now we have found mm, S for which you can go from I to K with positive probability in m plus n amount of states. And so yeah, this is a proof for to show that communication is an equivalence equation. So my final claim was so now what we'll say is we'll put them into classes. So we say that two states, if they communicate with each other, we'll put them in classes. So this is we're going to communication classes. So what we're doing is if two states they are in the same class, right? And two different classes will either be disjoint, because if one of the state from one class communicates with one of the state in the other class, that means that this other class also is completely in this class. So they'll be disjoint or they'll be exactly the same class. So there are some definitions that I'll introduce now. One is irreducibility or irreducible. So, Markov chain is irreducible if it has only one communicating class. Okay, so give some example 0, 1, 2, so on. Okay, here you go. Let me find it. So okay, so how many communicating class are there? So if you're at 0, Here, basically, you have two community classes. So this is one community class and this is one community class. Okay, so here I did a small mistake. Here it actually goes, the definition stated it goes both ways. So they communicate if for some n greater than 0, pi is n greater than or equal to 0, and for some m greater than or equal to 0, pjim greater than 0. This both ways if it goes, then we say that uh, I communicates with j. So what it means that you need to have a positive probability of going from I to j in n steps, and you'll also need to have positive probability of going from j to I in some m steps. Those number of steps doesn't matter, but you need to have some positive probability. So here in this case, you have this. So these two are the two states. You have positive probability of going from 2 to 1, but you don't have positive probability of coming back from 2 from 1 or 0. So the communicating class 1 is the set 0 and 1, and communicating class 2 is set 2. So this is not an irreducible Markov chain because you have two different communications. This is just definition. The definition states that you can classify Markov chains either they are irreducible or reducible. If they're irreducible, that means that the whole thing boils down to the same communicating class. And why is that important to study is because uh, is because um, is because there are some properties which say that uh, some properties are class relevant properties. So if you show that one state follows this property and you show that all the states which communicate with that state, so all the all the states in the same class will have the same property. So you need not prove it for all the other states. You just need to show for one state and you're done for the whole class. So this what do you say? State class-based properties. If you have a reduced Markov chain, you just need to show it for one state and you're done. And the whole Markov chain will have the same property that you have showed for that one state. But they need to be communicating with each other, or they need to be in the same communicating class. So next I'll define something known as periodicity. So state I is said to have period D if EIIN equal to 0 whenever n is not divisible by D. And D is the greatest integer with this property. So basically, you have the GCD of all the n's which is greater than or equal to 0. So suppose you have a Markov chain where 0, 1, 1, 1. So basically, and you start from 0, then all the even states will be occupied with 0 and all the odd states will be occupied with 1. So the positive probabilities, all the even states of it being in 0 would be 0. then you take all the GCD of all the numbers and you will see that this will have a GCD of 2. So the periodicity is 2. This will also have periodicity of 2. So yeah. So this is not a this the period of this is 2, and this is this. So yeah, this Markov chain, the states have period 2. The next thing is a state. If a state has period 1, then the state is known as aperiodic. So uh, next, what we'll say is periodicity is also a class property. So as you have seen here, that these both are from the same community class, so they have the same periods. So the periodicity is the same. So if they are from the same class and one state has periodicity D, then all the states in the same class would also have periodicity D. So yeah, so the proof for periodicity being the same class we'll see in the next class. Um, and also recurrent and transient states of the community class, those also we'll see in the next year. And then we'll see recurrence and transients also in the next class. We'll see recurrent state theorems and more about irreducibility and finite space theorem. We'll see all this in the class. So to just give a recap of what we saw in today's class, we saw 3 examples of discrete time Markov chains. And we saw one was Bernoulli process, one was simple random walk, one was Hellenfest urn. Then we saw how to calculate multi-step transition probabilities. One-step transition probabilities are given by the Markov chain. If you know the one-step transition probabilities, how to calculate the n-step transition probabilities. Then we saw Chapman Kolmogrov equations, which gave you a way to calculate the n-step transition probabilities by just multiplying the transition matrix. You get the n-step transition probabilities. Then we saw something known as communicating classes. So communicating classes. Um, so if you have a positive probability of going from state I to state J, with any n step probability, there is a positive probability. And also similarly, you have J to I, a positive probability with any M step probability. Then we say that those two are communicating with each other. We showed that this communication is an equivalence relation. That means it follows 3 properties: reflexivity, symmetry, and transitivity. And also we showed the proof for those, and we showed that communication is an equivalence relation. Next, we introduced something known as irreducibility. So uh, a class is set of all the states that communicate with each other. That is a class. So if a Markov chain has only one communicating class, then we call it as an irreducible Markov chain. There are examples where Markov chains can have different communicating classes. Then we also introduced something known as periodicity of each state. Uh, yeah, we'll do the rest in the next class. I'm stopping the